I think I have uploaded 2 tutorials. Have you seen that?
Yes, sir.
Please solve it. One day we will discuss tutorials. Okay, so if you don't have any questions, let's go to discuss how to you know get so last time I discussed it about flow methods, two flow method, like one is continuous flow and another is stop flow. So if price of chemical is not an issue generally, then we generally go through continuous flow method. But if price of the reactants are very high, then we generally use stop flow method. But the stop flow methods are generally confined to reaction uh, where like the time of completion is in microsecond to millisecond region, or microsecond to second region. Uh, but if suppose something happens faster than that, for example, most of the reversible reactions are very fast. In that case, you cannot use these flow methods. So in that case, what we need to do? So for that, what we generally use is known as relaxation methods. Okay, there are several different kind of relaxation methods. Uh, for example, when we use temperature, then that is called temperature jump. Similarly, we can change the pressure, that is called pressure jump, and then you can also change the pH. So the idea behind this method is, suppose this is a reversible reaction, A going to B, and this is very fast. Normally, I cannot measure the rate constants just by using normal methods. In that case, what we do is we uh, take measurement, suppose A to B, uh, just increase the temperature very fast. Okay, generally we do it by using laser. So what will happen if I increase the temperature? Then equilibrium will change, right? Equilibrium will change, and then suppose I remove it, then from the second equilibrium it will go back to the equilibrium which is at room temperature. So suppose this is a reaction. If suppose I increase the temperature, what do you expect? Whether B will be formed in larger amount or A? What happens to this reaction? In which direction it will shift? Can you tell me? Anyone?
So for
So if I increase the temperature, what will happen to amount of B? Equilibrium amount of B, I mean.
Depends on delta H.
Very good. So it will depend on delta H. So suppose it is an exothermic reaction, then what will happen if I increase the temperature?
A will be more.
What?
A will form more.
A will form. So equilibrium will shift towards reactant side. Am I right? So for exothermic reaction, B will go to A, and for endothermic reaction, A will go to B on increase in temperature. So there will be a different equilibrium value. So suppose at the room temperature it is A equilibrium 1 and B equilibrium 1, then what you expect that at higher temperature this will be A equilibrium 2 and B equilibrium 2. Am I right? And if suppose I now remove the laser, which is basically increasing the temperature, then it will again go back to this position. All right, so this is known as temperature jump. Similarly, you can play with the pressure and you can play with the pH. Anything which affects the equilibrium can be used, but you need to make sure that it happens very fast. That is the only thing which you need to keep in mind. Okay, so it is shown here that suppose it went to be equilibrium 2. It is basically B1 equilibrium, but here it is. So you applied the temperature, it went to let's write B equilibrium 1, then it relaxes back to B equilibrium 2. So that's what is shown here. All right. So this is at room temperature and this is at some high temperature. So some high temperature, it will go to B equilibrium, and then from that it is relaxing back because now you have removed the laser which is used to hit this system. Then it will relax back to final equilibrium stage. Okay, and now you are seeing that how this delta B changing with time. So it will relax back very slowly and it will be it will show like this. Okay, so this is state when it is heated to a particular temperature, and after that it is relaxing back. Okay, so so that's what you are trying to see, and this time period is this time period you are going to change, and this time period is equal to 1 by k1 plus k minus 1. I will show you how to get this tau, but now you can since so now you can get the this value by just fitting this with the curve. You will get the value of 1 by k1 plus k minus 1. An equilibrium constant can be measured in a different way, and when you know the equilibrium constant and you know this tau value, you can calculate the value of k1 and k minus 1. So now let's go and see how this relaxation time, which is known as relaxation time, is obtained from the fitting of this curve. Okay, so let us see. A is equal to, so if I take this reaction, A going to B, and this is K1 and K minus 1, then what I will write, dB by dt is equal to dB by dt is equal to, just one minute. Okay, dB by dt is equal to K1A minus K minus 1B. Okay, K minus 1B. And now you see here that when it started relaxing, okay, then at this time, if you look at here, this is delta A is equal to A equilibrium. So suppose, so let's write here. So A equilibrium is suppose here, and then it is relaxing. Then B equilibrium, then you can write that at a given time t, this is A equilibrium plus delta A, and this is B equilibrium plus delta B. And so there will be a relation between delta A and delta B, and that will be delta B will be equal to minus delta A. Am I right? It is quite simple. Now, what you can do is, in place of B, you can write simply, B equilibrium plus delta B. So that's what it is written, that, D B equilibrium plus delta B by dt. You can write dB by dt is equal to this, and since dB equilibrium by dt is 0, so this is equal to d delta B by dt. D delta B by dt. That's what is written here. And if you put A is equal to A equilibrium plus delta A, then you will get K1 A equilibrium plus K1 delta A minus K minus 1 B equilibrium minus K minus 1 delta B. And now K1, so if I write simply dB equilibrium by dt, What I will write? K1 A equilibrium minus K minus 1 B equilibrium. K minus 1 B equilibrium. And and this is equal to 0. So what I have taken is this 2 equal to 0. This minus K minus 1 B equilibrium is 0. So what you are left with? K1 delta A minus K. So what you are left with is K1 delta A minus K minus 1 delta B. And we know that delta B is minus delta A. So simply we can write this as, if you write this as a K delta B, then you just write this. And so you are left with minus K1 plus K minus 1 delta B. And now you know the solution of this, all right? So delta B is equal to delta B not, all right, and exponential minus K1 plus K minus 1 into T. All right, is this okay? Any question here?
Sir, can you please explain how did you write dB by dt as d delta B by dt again?
Okay, so yeah, how I wrote this? Okay, so B
Yes,
is
sir.
equal to what? B equilibrium plus delta B. Am I right? B equilibrium plus delta B. Is this
Yes,
okay?
sir.
So that's what I am writing. dB by dt is equal to dB equilibrium plus delta B by T. And dB equilibrium by dt is 0 because this is at equilibrium. So these all are constant. Right? At equilibrium, what we know that rate of product formation will be 0. Is it okay? So
Yes.
dB
Yes,
by
sir.
dt will be 0. So what is left? d delta B by dt.
Okay, sir.
So dV by dt can be written as d delta B by dt. Is this okay?
Yes, sir.
Okay, anyone else?
So the equilibrium is changing. So dV by dt, like at equilibrium also would change, right? Like concentration of V is also changing because we are adding some temperature to it.
Okay, so suppose at one temperature, if I increase the temperature at which this is the value, am I right? And now this will relax back to A equilibrium 2. If you remember here, what I told that we are first is this is the room temperature, this is at the high temperature. So what we did, we increased the temperature so that it gets A equilibrium 1, B equilibrium 1. All right. After that, if I remove the temperature source, right, then what will happen? It will relax back to room temperature value. All right. So it is going from this point to this point, relaxing. So now delta B is point here. You see, this is the point. All right. So that's what we are trying to do. So what I am saying that A equilibrium, it is relaxing back at some time when it has not fully relaxed. Then we can write this. There will be some change in A and there will be some change in B. Am I right? Concentration of A and B. So suppose I say this is delta A. Okay. And this is delta B.
Yes,
Okay.
sir.
So delta B will be minus delta A. Let me write in a different way. Probably you will understand that in a much better way. Okay, so let's take this reaction A going to B. And it is at A equilibrium and this is B equilibrium. What do we generally write? This is A equilibrium minus X. Suppose it is going towards this side. It can be opposite also. B equilibrium plus X. That's what we write.
Yes, sir.
All right. So dV by dt, what you will write? dV by dt is equal to K1 into A minus K minus 1 into B.
B.
And B equilibrium by dt, what I will write? Or dx by dt. Let's write at equilibrium, what I will write? dV by equilibrium by dt is equal to K1 A equilibrium minus K minus 1 B equilibrium. Am I right? And then yeah, so K minus this will be equal to 0. Is this okay?
Yes, sir, at equilibrium.
This is equal to B and this is equal to A.
Yes, sir.
So if I subtract this, what I will get? Dx by dt, B minus B equilibrium. This is B. B minus B equilibrium. I'm subtracting this. What I will get? K1 A minus A equilibrium. Am I right?
Yes, sir. Yes, sir.
Minus K minus 1 B minus B equilibrium. And this is equal to what? A minus A equilibrium?
A.
A minus A equilibrium. A is this.
Oh, A. Yes, sir.
Minus X.
Minus X.
Okay.
बैकग्राउंड में थोड़ी आवाज आ रही है, लाइक बैकग्राउंड में आवाज आ रही है.
आवाज नहीं ठीक से आ रही है?
नहीं, मेरे बैकग्राउंड में आवाज ज्यादा, बैकग्राउंड नॉइज ज्यादा, इसलिए ज्यादा बोल नहीं रहा हूं, लाइक माइक ऑफ.
Okay. K minus 1 into X. B minus B equilibrium. So is equal to minus K1 plus K minus 1, plus K into X. So dx by dt. Now you can solve it. Am I right?
Yes, sir. Thank you.
So that's what I was saying. Okay, so this is one of the reactions which I showed you how to do that. You can also think about that you should try at home. If suppose A giving you B plus C. For example, water dissociation. It gives you H plus OH minus. Okay, so can you calculate relaxation time? What is relaxation time basically? So if I solve this, what I will get? X is equal to X naught exponential minus K1 plus K2 into T. And this can be written like delta X naught exponential, sorry, it's okay, is equal to X naught exponential minus T by tau. So it is inverse of tau is basically called relaxation time, which is equal to, if you see here, it is equal to 1 by K1 plus K2 or K minus 1, whatever you, K1, K minus 1, am I right? So K minus 1. So this is your relaxation time, minus K by 2. This is your relaxation time. Okay. So through relaxation time measurement, you can know what is the value of 1 by K1 plus K minus 1. And since you know equilibrium constant, for example, water dissociation, you already know what is the equilibrium constant, then you can calculate the value of K1 and K minus 1. K1 and K minus 1. So for very fast method, you can use the temperature jump method. Similarly, there is a way to do pressure jump and there is way to do pH jump. So these are the three different methods which is used to measure rate constant for a very fast equation. Okay, is this okay?
Yes, sir.
Okay, so let us, yeah.
So in the final expression, shouldn't it be T minus T naught, where T naught is the jump time when we initiate the jump?
No. This is relaxation time, not jump time. Okay. So this is relaxation. Basically, this is This is after temperature jump. It is happening. Okay.
Yes, sir. But in the expression of delta B, I mean, we had delta B equals to del B naught exponential minus K1 plus K2T.
So this is del B naught. Am I right? And this is changing. This is decreasing with time. Okay.
Okay, sir.
Okay. So this is your equation. T by tau, and tau is equal to 1 by K1 plus K minus 1. Similarly, you can also derive equation for this and you try yourself. Here is the solution given, but you try yourself how you will get it. A plus B going to P, then delta P is given by delta P naught. Same equation we are using, exponential minus T by tau, but in this case tau will be 1 by K1 A2 equilibrium plus B2 equilibrium plus K minus 1. So please note it down. Please note it down and try to solve yourself. If you are not able to do it, I will help you. Okay. So please keep this thing in mind.
So A2 and B2 are the final equilibrium values, right?
Yeah. No, this is the equilibrium value. Okay. So this 1, 2 is a bit confusing, but this is this value. Okay.
Okay, sir.
Okay. So please keep that thing in mind. So this is value after the temperature jump. Okay, some people take first one as a 1 and some books has taken this as a 2. But keep that thing in mind. This is the value after the temperature jump. Okay. Okay, so these are the relaxation methods. So we have discussed slow methods. We have discussed fast method. So now we know how to calculate rate constant. For example, in the slow method, we will not be able to find out the value of any physical properties at time t is equal to infinity. In that case, what we should do, that we have already studied. Now for the fast method, what can be done, that you should know, because there are a lot of reaction which happens in less than 1 second, and it is not possible, humanly possible, to measure it by yourself. So you need special instruments, and there are also temperature jump instruments available in the market. And so for the fast reaction, people go for temperature jump or flow methods. So please keep that thing in mind. Okay. I discussed about how to avoid differential solving differential equation. There is one more things which you need to keep in mind, and that is what is known as pre-equilibrium concept. Okay. Pre-equilibrium concept, this is the equation, A going to I and I going to P. Okay. This is the equilibrium, and then equilibrium followed by a slow state. Fast step followed by a slow step. Now question is, can we apply a steady state approximation? If you remember, if first step is fast and second step is slow, can we apply a steady state approximation?
No.
No, sir.
Okay, anyone? Generally, if I go for this, A going to I and I going to P, if this is fast and this is slow, then concentration of I, am I right, will increase too much. And then I cannot neglect concentration of I with respect to A and P, and that's why steady state approximation cannot be applied. Right, but this is not the case when a pre-equilibrium, equilibrium is followed by a fast, slow state. Why? Because what we have to keep in mind that concentration of I should be small. If it is small enough, then I can apply steady state approximation. Now you see what is the difference between these two? It is forming fast, but then again it is going back very fast. Both K1 and K minus 1 is fast. And then I is going to P also. Okay, so this is, if this is fast enough, which is generally in case of reversible reaction, I can apply a steady state approximation. That's why I always say that you have to look at the concentration of I with respect to A and P. It is not always that if first step is fast and second step is slow, I cannot apply a steady state approximation. What I need to make sure that concentration of I remains low during the entire course of reaction. Am I right? In that case, if I suppose K minus 1 is also fast, am I right? Then I can apply di by dt. And generally it happens that the reversible reaction are fast from both sides. Okay, so di by dt is equal to K1A minus K minus 1I. Am I right? Di by dt. So I am looking at this, and minus K2 into I. This will be equal to 0. I can apply a steady state approximation. Okay, so what value I got? I is equal to K1 into A by K2 plus K minus 1. And I told that K minus 1 is quite greater than K2. Am I right? In that case, what will happen? This will be equal to simply K1 by K minus 1 into A. Am I right? And then you see, so now I even don't have to apply because I can simply write this. K is equal to K1 by K minus 1, that I know. But generally it doesn't happen if this is not the case. And you can see that it is like I by A is equal to K1 by K2 plus K minus 1. But suppose K minus 1 is quite greater than K2, then I can simply write equilibrium constant is K1 by K minus 1. And what is K? K is I by A is equal to K1 by K minus 1. So I is equal to, why we solve differential equation? Because I want to know the concentration of I. Right? K1 K minus 1 into A. It is quite simple. I can know this just by applying the concept from equilibrium. Only thing we need to make sure that K minus 1 is quite greater than K2. Then even I don't have to apply a steady state approximation. I can simply apply, I know that this equilibrium constant, which is K by K minus 1, K1 by K minus 1 is equal to I by A. And so I is simply K1 by K minus 1 into A. And this is a well-known pre-equilibrium concept. And a lot of the reaction in organic chemistry go through this step. So again, I don't have to solve differential equation. I can simply apply equilibrium concept to get the concentration of intermediate. See, so there are two tools available to you. One is to apply a steady state approximation, and the second is to apply pre-equilibrium concept. And that is the way in which you can avoid solving differential equation. But there are cases in which you have to apply, and you have to solve differential equation. In that case, I told you there is one of the way which I showed you is by using RK method. Is this okay? Any question here?
Sir, over here, like normally case में हम जब ऐसे से करते हैं तो फिर P product इतने हो जाता है कि like there's enough concentration of P and then it does not come back. That's why we can say comparative to P and A, I की कम है ना. पर like because when you're comparing, we say कि in comparison to P and A, I की concentration is really less. That's why हम उस पैसे से लगा पा रहे हैं.
Yes,
But
yes.
इस केस में initially ही P बहुत slowly बनेगा because K2 is much less than K1. तो फिर K minus 1. तो मतलब initially ऐसे लगाना मतलब possible नहीं होगा ना at the initial stages.
Okay, so generally you see that okay, you are right in the sense, but if you go to product, you know, final, I am talking about final concentration, maximum concentration. Okay, so that's where, and also keep in mind that concentration of I will not depend on product. Am I right? Concentration of I will depend on reactant A. So generally we see in comparison to reactant, but if you are looking at product also, that's okay. But product, then we have to look at the concentration at the final stages. Okay, when reaction is complete.
तो एक और डाउट है, लाइक ये जैसे ये एक तरह का इक्विलिब्रियम कंडीशन ऐसे और भी होते हैं क्या या फिर?
Yeah, there are a lot of reactions in organic chemistry which go through this kind of a step. Like first step is reversible and second step is the irreversible.
So first step is reversible and second reversible slow. Is this a standard pre-equilibrium condition or like?
There are a lot of reaction. That's why we generally teach it.
Okay, thank you.
There are a lot of reaction goes through this. Okay. So this is the way in which you can get the concentration of I, and once you know concentration of I, then you can also solve the you can also get the amount of P, because we already know how to solve for A. Okay. Now let's go to application of kinetics. Yes.
So can we, since we are saying that the concentration of I is much less than A, then does that mean K1 is much less than A, K minus 1?
No. What I said, sorry, what do you say? I didn't say concentration of, what I am saying that K2 is quite less than K minus 1. Okay. Means K minus 1 is very fast. Okay. In that case, what happens, that concentration of I remains very, and again, first thing is K1 and K minus 1, both are very fast. And then you can apply a steady state approximation, first thing. Because in that case only I will remain. For example, K1 is very large, but K minus 1 is comparatively quite small, then I will form in a larger amount. I'm not saying that. I'm saying that K1 and K minus 1 both are very fast. Okay. In that case, I will not be formed in very great amount. In that case, we can apply a steady state approximation. Now I am comparing K minus 1 and K2. If K minus 1 is quite greater than K2, I have already told this is a slow step, so it will happen. Then you even don't have to apply a steady state approximation. You can simply write this pre-equilibrium concept to get the value of I. Is this clear?
Yes.
कुछ confusion है बोलो. Anyone else? Yeah, please, one.
In this, we are only seeing K minus 1 and K2, right? Like for K1 and K minus 1, the only condition is that K1 should not be much greater than K minus 1.
K minus 1, you are right. Then I cannot apply even a steady state approximation.
Okay, sir.
Okay, so it is not that every reversible step followed by any this thing I can apply this pre-equilibrium concept. चाय में ना ज़्यादा चीनी मैं चीनी कम चीनी कम आलू ठीक थैंक्स मैंने खुद बनाई है वैसे थैंक यू वेरी yeah so is it okay?
Sir, what is the difference between a pre-equilibrium and equilibrium stage? Can you explain a bit?
Equilibrium तो एक ही step का हुआ, right? So I don't have to apply it there. There is no intermediate in that case. Okay.
Okay.
When there is intermediate, then I have to apply this thing. Otherwise, I don't need to apply because that is a product, right? Only product and reactant will be there. This is to get the concentration of intermediate. Is this
Sir,
okay? Yeah.
Sir, if the concentration of I is low, then if we apply steady state approximation, then we can get the concentration of I for any general time, right? But if we apply this equilibrium state, then we will get for the equilibrium at the time of equilibrium only.
No, it is not. I am saying I am getting at any time. Okay. I'm not saying that I will get only equilibrium value.
But sir, isn't it like that the equilibrium constant is equal to the ratio of equilibrium concentrations and the reaction coefficient Q is equal to at any general time?
Hello, can you listen me?
Yes, sir.
Okay, sorry. I think internet was bad. Anyway, so yes, tell me what you are asking. Is it okay now?
Yes, sir, your voice is audible. I was asking that the equilibrium constant is, I think, defined as the ratio of the equilibrium concentration, right? When the species has reached the equilibrium. So if we apply this equation, which is on the left, so we will be able to apply it only when this reach the equilibrium, right? Before that, it will be equal to Q instead of K.
Yeah, you can say that, but it is not exactly equilibrium, and that's why it is called pre-equilibrium. You can assume that A and I is in equilibrium. Okay, but I can get the concentration at time because there are very less amount going to product, and so at any given time it is like, you see, I and I equilibrium are not very different. Right, that's what is the case, that I remains constant during entire reaction. So you can say yes, I is around equilibrium value of I. Okay.
Okay, sir. And using steady state approximation, we can get at any general time, right? Because
For both you can get, you see here, again you see, I applied a steady state, am I right? What I got? K1 into A by K2 plus K minus 1?
Yes, sir.
But K2 is quite a small?
Yes, sir.
What I got? Exactly. Same thing. What I get from the equilibrium concept.
Yes.
And that's quite obvious because I will not be much different from I equilibrium. Am I right?
Okay, sir.
Yeah. After. Haan, theek hai. Thanks. Okay. Yeah, just I will start after the class. Okay. Sorry. Yeah. So is it okay now?
Yes, sir.
Okay. So let's go ahead. You see, these are the very important points because sometimes you don't have to go and solve for the simple reactions. You don't have to go and solve differential equation. And so it is very important. Okay, now next thing is, which is very important from kinetic point of view, is understanding the mechanism from the rate law. Understanding the mechanism of the rate law. So if I know rate law and I can get, for example, I can know what is the order. We have already discussed how to get the order of the reaction. Once I know order of the reaction with respect to a particular reactant or all the reactants in a reaction which involve more than one species as a reactant, then from the rate law, can I get the mechanism? Okay, mechanism of the reaction, and that is very important. Okay, so before I explain this, let's go and I will show you how to write rate of reactions for a complex processes. When you see that one of the application, I will show you in the complex reaction like protein aggregation. I show that and then I will also try to explain you how to get mechanism from the rate law. Okay, so this is kinetics of aggregation. Let me show you some complex thing. How we can apply this kinetics to different processes. Till now you have heard about how kinetics can be applied to an organic reactions or inorganic reaction. But now let's think about protein aggregation, protein aggregate. So a lot of neurodegenerative disease like Parkinson disease, those happens because some of the protein in our body gets aggregate with the age. Okay, and when it aggregates, these aggregates are toxic and they start killing cells, and that's why we start losing function with the age. Okay, so these aggregates, particularly when we are dealing with these neurodegenerative diseases, are a particular kind of aggregate known as fibril. Okay, so how does kinetics help here? So I show you that if you look at the kinetics, it will happen like this. So this is when there is no aggregate, and it starts when there is no aggregate. Then with time, it goes like this. Okay, this is known as lag phase. This is the time in which there is not very much aggregates has formed. This is protein aggregates. I'm talking about protein aggregates. And so you can think of, if suppose there is a Parkinson disease in someone or Alzheimer disease, generally it happens after like age of 50. Suppose it is a age of 50, then that is known as lag phase. But once it starts, it goes very fast. And you can see some aggregates, you can see it here. So it goes very fast, and after a certain time there will be saturation phase. After that, no more aggregation takes place, and then this is your saturation phase. So this is also kinetics, and we can look at the kinetics of this thing. We do regularly in our lab. Okay, so this is lag phase, this is growth phase, and this is known as saturation phase. So this is the time. So once, like after age of 50, it starts, and then it can deteriorate very fast because aggregate is getting formed very faster, and you will see that people start losing memory, people start having hand shaking and those kind of things. This is all because of the proteins, which are functional proteins in our body, starts getting aggregated. Okay, or form fibril. This is basically for fibril formation. Now, so sometimes we look at what is the mechanism. So generally what happens, why there is a lag phase? This is because the first step is the slow step. And what is the first step? This is the first step, which is known as primary nucleation. So in that, what happens that like few monomers, come together and then forms nucleus. So nucleus formation is very important. And this concept of nucleation comes in quite different phenomena. For example, crystallization. So if you want to make a crystal, then nucleation should happen. If nucleation doesn't happen, crystal will not form. So this is your rate determining step because this is a slow step. Okay, so suppose nucleus formation happens through like 3 different monomers comes together and forms a. So this, if in this case NC, what is known as N number of monomer for critical nucleation is equal to 3 because there are 3 monomers. Okay, and now what happens that this monomers form and then they start elongate. And generally end to end happens. It means that if this is the suppose fibril, then one monomer can come from that side, one monomer can. So from two sides only it will grow. And that process is called elongation. This is K plus, and that is shown here. And then dissociation can also take place, like one of them are coming out. Now how?
Fibril कैसे पहुंचते, like similarly single addition, or will they even add?
Yeah,
like
3 के बाद सारा single होगा. Okay.
Nucleus
3 के बाद 4, 5, 6, 7, 8 ऐसे बनता जाएगा. But these are the fast processes compared to this. And that's why you see this, there is a lag, because in lag there is a formation of nucleus. And this is a very slow process. That's why this disease starts after, a certain age. But जहाँ ये nucleus form हुआ, then other monomers which is in our body, they will come very fast, and then there will be a very fast growth. So Kn is very fast. This K plus is, Kn is very slow, and K plus is, very fast, large number. So, so this process will happen very fast. Dissociation, but this is again slow thing, and so so most important thing is K plus is very fast, and that's why there is a what is known as log phase. In log phase, this fibril grow very faster. Okay, so how do we suppose I need to apply kinetics? How I can do that? Okay, so generally what we generally write is df. F is fibril as a function of, so suppose J size, and this is T at time T by dt. That's what we calculate. Okay. For that, what will be the thing? Okay. So here it is written the first step, the equilibrium, the rate. What I will write? d f j T by dt will be equal to Kn. This is the rate constant for this process. Mt power Nc. So this is monomer at concentration time T and power Nc. Nc is what? The number of this thing. Okay, Nc may be 2, Nc may be 3 or 4. So here Nc is equal to 3 because there are 3 monomers. So you can put 3. And to delta. Delta JNc. What does that mean? This is Kronecker delta. Have you heard about that? Kronecker delta?
Yes, sir. Yes,
So
yes,
if J is equal to Nc, then it will be, value will be 1. Otherwise it will be 0. Okay. So if del is, in this case, if J is equal to 3, then this will have a value 1. So it will only contribute to the fibril of size 3, not to other. Am I right? Now go to elongation process. This is your K plus. So you see one monomer and one fibril. So that's what it is written, that MT K plus into MT into this fibril. What is the size of fibril? J minus 1. Okay, this is the in these steps I have taken J is equal to 7. So how J plus J is equal to 7 will form? It will form from 6, and this is the equation, MT into K plus FTJ minus 1. And now I am using 2. Why this 2 factor? Because this can come from this side, this can come from this side, both ends. And so this is the kinetic term if I am taking J is equal to 7. So J is equal to 7 is formed from J is equal to 6. Now this is elongation process, but sum of J is equal to 7 will go to J is equal to 8 by this same process. So concentration of J is equal to 7 will decrease. And so I am writing minus 2 MT K plus FTJ, because here you see size J is involved. Now dissociation process can happen, K off. So one is getting, so from dissociation process also J is equal to 7 can form from J is equal to 8. and that's what is written here. And similarly, j is equal to 7 can go to j is equal to 6. So this value, okay, this will be minus, sorry, minus is missing, but here you see this is minus value. So you see, for one complex process also you can write, I just wanted to show you because, this for a very complex process also you can write, kinetic equations. Is this okay? Is it clear? How do we do that? Okay. So if it is clear, let's go and explain one more thing. So now in the lab, if you are looking at, I don't calculate, we don't see how this number is, fibril concentration is increasing. What we generally see is how fibril number and mass is increasing. That we can see in our lab. Okay. So what is the number? Number is simply given by PT, which is sigma j is equal to NC to infinity the number of fibrils. Okay. So below j is equal to NC, I don't say that as fibril. For example, in the last case, like if j is equal to 2, then that is not a fibril. From j is equal to 3, I start counting as a fibril. So that is the number and mass. What is mass? Mass is equal to j into j is equal to NC to infinity j into FTJ. Why I'm multiplying by j? Because the size, for example, in this case, this has 5 mass unit. 1 fibril, but there is a 5 mass unit. So what I am taking, if this is the size FTJ, then you multiply by j. So basically take this, multiply by 5. That will give you mass. Now here I have shown you several different things. Okay, so these are suppose the form fibril with monomers in the solution. Then how I will calculate PT? You see, I will not count this because this is monomer, this is monomer, this is monomer, this is monomer, and this 2 and these 2 are also not fibril because this is less than NC is equal to 3. So how many fibril number? 1, 2, 3, 4. So there are 4 fibril number. And what is the mass? This 4. What is fibril mass? I'm talking about fibril mass. Keep that thing in mind. So 4 in this unit, 6 in this unit, 10, 4, 14, and 5, 19. So this is what I am writing. 4 into 2 because there are 2 fibrils of 4 size. So 4 into 2, that's what comes from this. 5 into 1, this is 5 into 1. And this is 6 into 1. So 19. So this is, one is number, another is mass. And that can be seen in the lab. Now, if I write dpt by dt, means how PT is changing with dt. So remember, you have seen all the processes. Am I right? If you go here, which is the process which is making a fibril? Only this process, number, changing. Before that, it is not fibril. Here, this is fibril. In this process,
already a fibril.
Change is not changing. Number is not changing because you are going from one fibril to another fibril.
Yes.
In all these steps. So number is changing only in the first process. So that's what is written here. But mass, how does mass change? Okay.
Can't a nucleus dissociate? Like.
No. So you see, this is not a reversible process. Okay. So that's what we are assuming in our hypothesis. Okay. Now you see here. Here mass, how mass will change? First step will also change the mass. Okay. First step will also change mass. but most of the mass, because this contribute very less to mass because this is a very small number. So what we generally do, we take only elongation process as which can increase the mass of the elongation. Means elongation process, we just assume that that is changing the mass. So there is assumption, but certainly this can also come. In comparison to this is not changing the mass, and that's why we are taking this. And now you can solve this. This is two equations. You see, this is PT. Why we are taking PT into MT? Because each fibril will react with one mass. So number. Okay, so into MT. So this is the way you, now you have a two equation, you solve this, and then you can get, in fact, this is the solution of this, that MT is your mass of fibril. This is the monomer concentration, and then this it depends on this lambda value, which is the multiplication of Kn and K plus. We have neglected this K off. We generally this doesn't happen and happens very slow. So K off is generally neglected. That's what we did, and that's why it is not coming into this equation. But there are equations which also includes the K off also. But this is one of the solutions. So what do people do? That if you observe something, they try to fit with this equation. Experimental observation, you can look at MT with time t. If it fits this, then they say, okay, this is following this mechanism. But this is not the only mechanism. Okay? Is this okay? Now, what other things can happen? Like this is fragmentation. This can also happen, that it breaks here. Then there is a nucleation also can happen from this. There is a branching here, and then so now you can see here that if this happens, what happened? Now we have two fibril, and now elongation can take place from both sides. पहले दो ही जगह होता था, but now you can see that it can happen in a 4 different ways, and that's why there will be growth of aggregate will be very fast, because now you have 4 ends at which monomer can add. In this, monomer can add from 3 different ends, and this is known as monomer dependent secondary. So this is also nucleation process, and 3 goes. So another nucleation process can happen, then one branch can develop from there. And for that, you can, these 3 processes, you can again write the rate distribution, rate distribution term. And then you can write dp by dt or dm by dt, and you can solve it. So if suppose that this first equation is not able to give you a very good fit, then people go to second equation. All right, and after second equation, for a fragmentation, there will be a different term for MT, and for secondary nucleation, different term for MT. And now by fitting the curve with the 3 different equations, people can know whether it is a simple, the aggregation can happening in a simple, what is primary pathway or through secondary pathway. In secondary pathway, they can understand whether it is a monomer dependent secondary nucleation or fragmentation. So idea is this is the way people do in several different branches of chemistry, biochemistry, or other things, to look at the mechanism. Mechanism is very important. We have already seen, in our organic reaction, knowing mechanism is very important. And so this is one of the way that you solve the differential equation. You try to fit, you develop a model, then solve the differential equation for that, and then you try to fit your experimental observation. If your model is true, then you can get a very good fit. If your model is not right, then your fit is not good. Okay, fit is not good. So I will stop here. You have any questions, just let me know.
So in the fifth slide.
Yes.
So in the fifth slide,
Yeah,
the mass is represented as J times FTJ. So like in the for fibril number, we were basically adding the fibril with different monomer values. Now, why are we multiplying the number with the number? I mean,
so you see that these two are fibrils. Am I right?
Yes, sir.
This 4-1 is a fibril. This 6-1 is also a fibril.
Yes, sir.
Do you think that mass will be same?
No, sir.
It will be different. How much it will contribute? 4.
J times.
4 units. Yeah, J time. And this will contribute 6 times. 6 units. That's what is done here.
Then also, what does small mt represent? Monomer
small
concentration.
mt monomer concentration. Okay, it is monomer concentration. So basically, this MT plus big MT, this is aggregates, and this monomer will be equal to initial monomer concentration. And that's why so DMT will be M0 minus MT. Is this okay? तो मोनोमर सारा ये मोनोमर ही कर रहा है, 4 मोनोमर आए थे, तो that's what I am seeing. Okay. Yes, okay. So and then this empty tells about the free monomer, and this empty tells you about monomer which is in fibril. Is this okay? Do you understand why this thing?
Yes, sir.
इसलिए मैंने एक एग्जांपल देके बताया है आपको. ये देखो, ये फिब्रिल में नहीं कंट्रीब्यूट करेगा, ये भी नहीं कंट्रीब्यूट करेगा, बिकॉज इट इज J is less than NC. The number is 4. Fibril are 4 in number, and this is what is changing, which is given by this equation. So for example, this 3 will come and form a fibril. Then number of fibril increased by 1. Mass कितने से change हो जाएगा? Because 3 has come, and so mass will change by 3 units of fibril. Mass of fibril will change by 3 units. Is this okay? A mass of monomer will change by just negative of that. Isn't it?
Yes, sir.
Yeah. Any other question?
Sir, in the last second slide where we are attaching that fibrils in the secondary pathway, can we no, in the above this, yes, no, below this.
This one?
Yes.
Okay.
In the last one, can we somehow control where the fibrils are attached?
No. So it can only come from two sides. Okay. Here we cannot control, but what we are trying
in the last one, in the C process.
Yes. So again, this is like NC, but since this is secondary nucleation, that's why we say K2. So this is called secondary nucleation. In secondary nucleation, you will need monomer plus fibril.
Sir, so can we like control where the monomers are attached to the fibril?
No, we cannot control. We can only only break this thing using inhibitors. We do that, and that's what people do. That how I can go and stop this secondary nucleation. Right, okay. That can be done. People can know. There are ways to know where it is attaching. Okay, which part of the protein it is attaching, but it is difficult to say that which monomer it is going and adding. Okay.
So each monomer is a protein. Can we say that?
Yeah. In
So
this case,
when
particularly,
this kind of structure is formed, will we call it like a secondary protein, like when we learned the tertiary quaternary proteins, like how they wrap each other in dimensions. So what is this process called? Like
this is secondary nucleation process. So protein, protein. You see, this is not unfolded protein,
okay,
but this is a kind of, you know, active protein also doesn't go like that, but there is some changes happens with time, right, in protein. And then, for example, mutation. Have you heard about mutation process?
not exactly.
Not exactly. So what happens that one amino acid changes?
Okay.
Or there is like a stress in life. So we all have a stress in life.
Yes.
And that results into, some of the protein getting, like not in their actual state. For example, in lab, if you try and increase the temperature or pressure, conformation of, so that is also a kind of a stress, right? So when you do that, then or add some molecule which may be formed because of, dysregulation of our biophysical process which is happening in our body. So those molecules can also affect the protein, and protein, if it is not in right state, then it will go aggregation, and that happens. And that's why in the old age we get so many problems. This all happens because of this neurodegenerative disease.
So like one small question, like if no one has any other question, that if suppose this process we can identify that it's endothermic, so then if a person lives in a cold place, then he'll have lesser probability of having Parkinson if the ambient temperature inside his body is able to maintain. Like if the temperature inside the body can be changed and regulated, so is it possible to reduce the chances of having Parkinson if we change the temperature of our body? Like maybe, I mean that's not sounding that logical, but would it factor in? Like if you can say.
Yeah, everything you see, it is very complex thing, and it is very difficult for us to tell right now that what are the factors, and that's why a lot of research is going in this field, and people are still trying to understand. You see, there is no drug available for this kind of disease right now. Just one recently for Parkinson, probably, or Alzheimer, one drug was approved by FDA. Okay, recently, but there were a lot of controversy regarding that. Have you heard about one drug recently which has come out in US? Hello?
No, sir.
No. Okay, you can see that, but
Okay.
there are means understanding. You see, any like our body itself is such a complex thing. Understanding that is very, very difficult. And that's why we are not able to get drugs for a lot of diseases. But a lot of good discovery in biology is not done by physician. It is done by physicist or chemist.
Yes.
Do you know that? Am I right?
Yes,
DNA
sir.
structure itself was discovered by chemist, one physicist, one chemist. So, these things are very important. Like I showed you that even mathematics. So all three are like, if you really want to tackle a very good problem, then you have to understand all three branches of chemistry. In fact, biology also, because unless you understand how things are going, what are the things involved. But even for understanding biology, you need physics, chemistry, and math.
Yes.
Yeah. Okay, so I will stop here. Okay, so in the next, you try to think about how you can write dp by dt and dm by dt for this process. Think about that. Okay.
So
So
will be any
this
reference material to read this from? Like
what?
if is there any reference material to read this, like if you want to read?
Yeah, actually, we have recently written, one review. So what I will do, I will put this, but that is very complex. And so, but you will be happy to know that one of your senior is also involved in that. Okay, Gargi Sharma, Gargi.
Okay.
Do you know her? No.
No, sir.
Okay. But I will share that review. It will be complex, but if you can understand, that will be really good. Okay. So I will stop.
Thank you, sir.
Thank
you, sir.